Welcome to solverfy.
All right. In this problem, we're given this wave function, which is of the form a e to the negative bx for x greater than 0, and a e to the bx for x less than 0. So this is just a symmetric decaying exponential, and we are given the value of b. It's simply 2 inverse meters, and we know that this capital A is going to be greater than 0. We're first asked to find the value of a, big A. We're going to use normalization to accomplish this. We're then going to sketch the wave function. And then we're asked to compute some probabilities for locating this particle represented by the wave function, psi. We're asked to find this probability of locating it in regions between the origin and half a meter, or 50 centimeters. We'll just say half. We're asked to find it for x just on the entire left side, less than 0. And we're asked to find it for this probability for half a meter to a meter. So these are our three regions. The only real equation that we'll need for this is to make note that the probability density function is defined as the complex square of the wave function, which normally, in the most general case, is the wave function multiplied by its complex conjugate. But in this case, we don't have any complex valued anything to worry about, so we can simply square the wave function. And of course, the normalization condition says that when we integrate up this probability density over all space, which in one dimension is just integrating in x, when we do this, it needs to equal 1. So if we integrate over all space, the probability of locating the particle in all space is 1. That's what normalization says. So let's first find A using normalization. Yep. So we know that by normalization, we need to integrate, if we integrate over all space, our wave function squared, it is equal 1. Now, because this is a symmetric decaying exponential wave function, we can make use of a trick using the symmetry that we don't need to integrate from infinity to negative infinity. We can simply integrate from 0 to infinity and multiply by 2 because it's symmetric. And specifically, what this square looks like is a squared e to the negative 2bx. I've simply squared the wave function. So this is our integral to compute. It's just a decaying exponential, so it's relatively straightforward. 2 big A squared. This integral of just a simple decaying exponential. Oh, that's a b. Boom. Okay. So doing that integral, we end up and rewriting this equation. We have 2 big A squared multiplied by negative 1 over 2b e to the negative 2bx, evaluated from infinity to 0. And of course, this comes out to, because the decaying exponential at infinity is simply 0, and at 0 it's 1. We have 0 minus 1 over 2b, which of course makes it positive. And simplifying everything, we have big A squared over b. Thus, A must be the root square root of b, which means our wave function, once normalized, is root b e to the negative 2bx, or e to the negative bx. Okay, so just a simple sketch of the wave function. This is part B. It's a decaying exponential on both sides of the origin, so it's some spike-looking distribution. This is pretty common. And B is controlling the decay rate. If B was larger, this would be much more spiky. And that's really it. So let's compute these probabilities. So the probability of locating this particle between the origin and half a meter, I'll leave off the units, just makes things a little simpler, is the integral of 1/2 from 0 to 1/2. This is the region of integration of our probability density, the square of the wave function, which would in this case be b e to the negative 2bx dx. And doing this integral once again, we would end up with negative 1 over 2b e to the negative 2bx, evaluated from 1/2 to 0. So we would end up with negative 2b e to the negative b. Minus a minus would give us a plus 1 over 2b. These are just inserting our integration bounds. We can pull the 1 over 2b out to give us a 1/2 and rearrange this a little bit. We end up with 1 minus e to the negative b, which for b equal to 2. We end up with a value of about 0.43. So this is actually pretty significant because if this is symmetric and we go from 0 to 1/2, then if we included negative 1/2 to 1/2, we would have over 80% of the probability. So this particle is pretty localized within this region. So this was part 1 of C. Now, we don't even need to evaluate the integral for the second part, where we're asked to find the probability of finding on the left side, rather. So if we're looking at the entire left side, and this is a symmetric wave function, its square is going to be symmetric. Thus, the probability of locating it on the entire left side has to be 50%. It's either on one side or the other by symmetry. So that would be 0.5. So that one's relatively straightforward. For the last one, we go from half a meter to a meter. We would repeat this integral 1/2 to 1 of the same probability density. We would end up with the same sort of integral. Everything would be relatively the same. So I'll skip a couple steps. We would end up with this. Okay. And for b equal to 2, we would have value of 0.058. It's about 5%. So you can see by this result and this result that most of this particle is pretty centered near the origin. We would expect to see it in the first half of a meter with a pretty high probability. And as we go further away, the probability decays pretty quickly. So that's it.